physicists, just wanted to go through these level 10 questions from the Introduction to Energy Bar Charts Pear deck that you worked on. So this was question 1. It says a 1,000 kilogram roller coaster car moves from point A to point B and then to point C. In the slide right before this, you worked on the energy bar charts themselves, and then this last question asks you how fast is the car going at point C? Now, it may feel like there's not a lot of information in this problem, but it's actually all there. So let's take a look at how we can go about this problem. So we are focused on 2 points. We're focused at point A and point C. And I think that in the slide right before, it says that we're going to take point C to be our lowest point. I'm going to go ahead and call that h equals 0 right now, just so that I don't forget, okay? If we do that, that means that the gravitational potential energy at C is 0. You can see from the bar chart in position A that we have 6 units of energy to work with. It's a closed system, which means the total amount of energy at position A has to be the same as at position C, which then tells me that I need to have 6 units of energy at position C, and they're all going to be kinetic. Okay, so that's kind of the first step in approaching this question. Now we want to go ahead and write down our conservation of energy statement that goes with this. So I'm going to start just from the basics, that the total energy at A equals the total energy at C. Okay, so I've got gravitational potential energy at A plus kinetic energy at A has to equal the gravitational potential at C plus the kinetic at C. Now you might be saying, hey, Miss Carbeling, but you just said there was no gravitational at C. I know, we're going to get rid of that. Just want to make sure that we're staying as completely transparent as possible. Okay, now this is the piece that might be the missing piece from the puzzle if you've worked on this problem already. And that is that you have to look at the bar chart for position A. There's a clue in there. If you take a careful look, you will see that we have the same amount of energy in gravitational that we do in kinetic energy. We can calculate the amount of gravitational potential energy at A, and then we'll just double it to give us the total energy at A. So let's go ahead and calculate the gravitational potential energy at A. So E sub g at A is going to equal the mass times the gravitational acceleration times the height at A. So these are all at A. The mass is 1,000 kilograms. The acceleration due to gravity, I'm just going to use 10 meters per second squared. And the height is right here, 15 meters. So now we can do some multiplication. Pretty simple multiplication for us. We've got 150,000 joules. It's kind of a lot, but we're talking 15 meters up and we're talking 1,000 kilograms, so it makes sense. Okay, so I've got 150,000 joules of gravitational potential energy. So that means that this right here is 150,000, which means this is also the same amount. So this total then is going to be twice 150,000. Okay, or we could, do that multiplication and find that that's 300,000 joules of total energy. Now, at C, we know that that's all kinetic energy, so we can say that that's equal to 1/2 the mass of the roller coaster times the velocity squared. And using that, then we can go ahead and solve for V. So we can say that the velocity at C, should put that little subscript in there, is equal to, that's going to be the square root of 2 times that total energy, which was 300,000 joules, divided by the mass, which was 1,000 kilograms. Okay, so we can do some quick multiplication and find that 2 times 300,000, I could probably do this in my head, but sometimes I don't trust myself, divided by 1,000 is 600. I'm going to take the square root of that answer, and I get about 24.5 meters per second. So again, the principle here was pretty straightforward, right? It's just conservation of energy. The piece that you had to catch was right here from our bar chart. That clue made it all easier. chapter. Thanks, guys.